Thank you very much. Our third speaker is Robert Bolin, and he's the Senior Vice President of Skyscraper Hennessy Group Chicago. And Robert's going to be talking about balancing energy, air movement, daylight and comfort in Atria in tall buildings.
My topic for today is really about Atria. And there are many different definitions of Atria that exist out there. And suffice it to say, I mean, for this particular type of element that goes into a building, essentially it's describing a multi-level space, often with a glazed roof and wall or walls, and usually adjacent to or near the building's main entrance. Atria are described to give a building a feeling of space and light. And while not a specific topic of this presentation, I think there are other topics or other presenters that are going to be speaking more specifically about the fire life safety control of super tall buildings and by association Atria in tall buildings. Certainly with regard to the design of Atria, those are some very important components, and I'll touch briefly on some of the things specifically related to ventilation associated with that. I often, when I'm talking about buildings or building systems or components of buildings, I like to think about, metaphorically, how it may be represented by something in nature. In this particular case, the anatomy of an atrium as compared to the human body. That metaphor leads us to viewing the atrium itself as essentially the heart of a building. So we're provided with a sense of welcome and hospitality for the building users and the visitors. The Atria, through its signage and information, provides a sense of wayfinding to other spaces throughout the building. It provides opportunity for informal gathering, for more formal gathering within a large volume space. It can take a variety of different occupational aspects. It can be a transition space. It can be a more regularly occupied space. It quite frequently provides your vertical transportation in the space. You've got your elevatoring and your stairwells that are directly adjacent to the atria. And when designed properly, it certainly can provide a level of excitement, a very lively space that can be wonderful and beautiful. But how to make it appropriately habitable oftentimes becomes a bit of a challenge. So some of the key elements from an indoor environmental perspective that significantly impact the usefulness and habitability of this feature requires a careful balance of several different things. So we've got light, whether it's natural daylight that we're trying to flood the space with, whether it's electric illumination that we're trying to supplement that natural daylight with. There's energy and water, obviously, that's required to heat, cool, humidify the space to maintain thermal comfort. And thermal comfort, of course, is ultimately what we're looking to achieve within the atrium from a mechanical engineering perspective. So I'm going to kind of go through those one by one, and you'll see how they hopefully come together in a balanced design approach. So the first one is certainly an extremely difficult and perhaps the most important element, which is light. Whether you're talking about an atrium or really any other type of space in a building, the issue of light, and more specifically natural light, becomes one of the most important aspects of any design for it to be especially habitable. So why, of course, is natural illumination so important inside of a space? Well, you've got the obvious energy issues associated with that. You bring more daylight into a space, you can dim or shut off the electric lights. That saves energy, creates less load inside the space. Less load means you have to have less conditioning, so it reduces energy on the HVAC side as well. So there's a lot of things that, certainly from an energy perspective, that come into play. But there's also things from a physiological perspective that goes to a person's sense of well-being. If in a space that is naturally lit, there's that sense of connection from inside to outside that that in fact plays with the biorhythms through a person's physiology. Now, an atrium, from a daylighting perspective, it's not as simple as just throwing a bunch of glass in the ceiling, or have a glazed roof, or have glazed wall or walls. It really has to be very carefully controlled, and the reason for that is sort of multifold. I mean, we've got the energy that, in addition to the lighting energy that comes in, we need to be careful, certainly with regard to the solar gain that comes in, which becomes a pretty significant load inside the space. But we also have the adjacencies that this atrium is butting up against, and how that atrium is actually being used from a lighting perspective to share light with other spaces, like you can see in the image on the lower right-hand corner. That's an atrium that's sharing daylight with office space that's adjacent to the atrium itself. Now, physical as well as computer simulation can and should be used early and often to tune daylighting design of an atrium. The images on this slide that you're looking at illustrate an atrium concept in which simple ray tracing modeling was used during a competition phase, really to look at several different alternative top lighting strategies for this particular case. The goal here was to obviously direct daylight deeper into this top atrium, and allowed us to look at different rooftop configurations, different reflector configurations at different times of the year to see what was most effective actually to drive daylight deep into that space. Certainly what we're finding, and hopefully a lot of you in the audience are finding, is that even at concept stage, these kinds of studies are being done to help you at least formulate even the initial strategy of daylighting for your atria. Similarly, daylight modeling to look at illumination levels, to look at glare control is becoming pretty simple with computer simulation tools. This type of analysis helps advise on external shading, which you may or may not be incorporating into your atrium. Internal glare control devices, again, shades inside of a space, that's a glare control device. That's not a solar shading device, because that load is now inside the space. But control of glare inside the space for visual comfort becomes increasingly important, because visual discomfort from poor glare angles frequently will manifest itself as a thermal discomfort of the occupants. So not only do you potentially have the thermal discomfort of the solar gain that is coming in, but you also have thermal discomfort that's associated with the light energy that's coming in and is essentially creating glare for the occupants in the space. These tools, very simple computer simulation tools, really give you the opportunity early and through the design process of looking very specifically at different sides of your space, different times of the year, so that you can determine a controllable deployment of solar and glare control devices. Next category is air. And of course we need to provide ventilation. We need to provide ventilation for several different reasons. Generally, we're trying to maintain an appropriate indoor air quality. Good indoor air quality for the space also goes to thermal comfort. We're trying to dilute the indoor air pollutants that exist within the space, coming off of the materials in the space. We're also trying to provide ventilation air for human occupancy within the space. And of course, we have the requirement in smoke evacuation mode, fire smoke mode, of needing to provide ventilation air for makeup air that needs to be part of the smoke control strategy. So there's many different ways to bring that air into the space. There are conventional solutions. Overhead and sidewall diffusers are a very conventional solution. Displacement diffusers we're finding more frequently, especially at the low level of the atrium. They're being used more frequently in atria around the world. as a means of providing a low level of indoor air quality. We're also seeing projects of ours where we're using a cascading ventilation scheme whereby you're actually taking ventilation air from adjacent spaces and cascading that into areas such as circulation spaces or balconies that then find its way through the airflow pathway out into the atrium and is then removed at the top of the atrium. So there's many different ways to sort of go about doing this. And I'm not going to go into a huge amount of detail about natural ventilation alternatives because I think there are some other speakers that are presenting on natural ventilation. I think one of my colleagues is speaking on natural ventilation for tall buildings, but specific to atriums, I think Anthony Wood is presenting something tomorrow related to the working group study the work that's been going on with regard to naturally ventilated buildings and atriums. But just suffice it to say that there are certainly projects out there that have incorporated natural ventilation as a means of providing this ventilation air, both at under natural conditioning mode as well as under smoke evacuation mode. But as one of the delegates in the audience sort of rightly pointed out, this is very, very tricky, certainly to do in super tall buildings or even tall buildings because you do have the stack effect that absolutely needs to be part of the consideration. So as you're going through any sort of an analysis looking at how temperature stratifies or what your distribution scheme is, you absolutely have to look at the stack effect both in summer and winter because you have things that switch quite frequently depending upon what your specific geography and its climate might be. And how that relates then to how you're supplying the ventilation air. Here's a couple of examples of projects. A very recent project and one not as recent, but who utilized natural ventilation in a mixed mode strategy. So for certain periods of the year, the buildings are air conditioned, other periods they're heated, but there are significant amounts of time in these very benign climates where natural ventilation is certainly utilized as the primary means of conditioning. So you've got the Manitoba Hydro Place in Winnipeg, which uses the atriums as part of a conditioning strategy that also conditions the adjacent spaces, which is very similar actually in some ways to what's happening in the Commerce Bank project, whereby the Sky Gardens are attached to multi-level atriums that are, again, also part of the inlet and outlet, not just for the Sky Garden areas themselves, but also for the occupied space. So just a quick word then on the atrium smoke control issue. So code requirements generally are going to dictate the ventilation airflow requirements, regardless of whether you're naturally or mechanically ventilating the atrium. The rational analysis that fire life safety consultants will provide is typically considering the stack effect, it's considering the fire temperature and fire size. It's considering the external climate and the wind conditions prevailing as well as other wind conditions. It's certainly considering the type of HVAC system and then the duration of operation in the smoke control mode. So, this becomes a very sort of important component then of how you're normally ventilating your atrium and whether or not you're providing a dedicated smoke evacuation system as part of the overall design, or whether you're integrating it with the existing HVAC system. So there are certainly some controllability complexities that need to be addressed with regard to that. I personally am a fan of providing a completely separate smoke control system from your HVAC system. It certainly gives you a better opportunity to take advantage of mixed or multi-mode types of ventilation strategies in the atrium. Okay, and energy and water is obviously tied to the ventilation because the ventilation is a part of the heating and air conditioning system generally. So whether it's an atrium or an office space, as is illustrated here, there's loads inside the building, and And while we in the HVAC community were often sort of bashed over the head about, the HVAC system needs to be more efficient. We kind of make that more efficient. That's what needs to happen for us to get to net zero. Well, yes, that's one thing that needs to happen that gets to net zero, but the HVAC system is sized to overcome the loads that are in the space. So those loads need to be driven down for us to be able to downsize HVAC systems, for us to be able to rely on alternative HVAC systems, for us to be able to incorporate natural ventilation as a normal operating strategy. So, it's the usual culprits, right? We've got the envelope gains and losses, and certainly with regard to an atrium, those are quite frequently 90 or more % of the loads inside that space are due to the glass that's associated with the atrium. Now, that's a little bit of a generalization, but if you've got a glazed atrium, that's where the loads are, and that's what has to be overcome. And then the heating and cooling system, similar to the HVAC, there's a variety of ways to heat and cool the building. We've got our sort of fairly conventional all air and air and water-based systems, VAV, fan coil units, these kinds of systems that are tried and tested. More frequently, we're seeing decoupled systems that incorporate radiant and convective hydronic heating and cooling systems that are combined then with displacement ventilation or a separate dedicated outside air ventilation system as a way of providing thermal comfort, heating and cooling to a space in a significantly more energy efficient way. It's interesting when you think about or investigate the actual heat capacity of the two different mediums for conditioning, right? Water has 3,400 times the heat capacity of air. So, we're talking about using generally small pumps and pipes rather than large fans and ducts as a way of providing comfort cooling to a pretty significant space. We don't want to forget the opportunity, certainly with regard to if your orientation works out and if it's appropriate for your geography and you have a heating season or you're in a heating-dominated climate, the opportunity actually to tune the building envelope associated with the heat, with the atrium to passively heat that atrium. And as with the ventilation, the ability to cascade from adjacent spaces. So if you've got circulation space around an atrium, and I'll show you a couple of diagrams of that here in just a second, ways to use that sort of cascading approach so that you're taking energy from one space, transferring it through another space, and then relieving it out through the top of the building. Okay, a couple of quick CFD animations here. I'll try and describe these so we're all clear on what we're looking at. Case 0 is sort of the base case. It assumes that all of the loads in the space and sort of setting the stage here. These are all the same atrium, just a super tall atrium. The assumption is the south-facing glazing, which is on the right-hand side. That is the glass wall. The other three sides are enclosed by the building. And it's got an opaque top. So the bulk of the load that you're going to see appears actually on that west elevation. Sorry, on that on the right side elevation. So the 0 case assumes that all of the loads in the space, solar, people, lighting, all of the loads are offset by all of the ventilation air that is conditioned being put in at the bottom. Okay, so that case 1 has the same loads. Actually, all 4 cases have the same loads. Case 1, we basically said, okay, let's allow the space to stratify, and let's just put half the amount of air needed to condition all the load in that space in at the bottom. So what you see in these temperature clouds is that the very high temperature in red appears much further down toward the middle of the atrium on that south-facing wall than it does in the base case. But also what you're seeing is that in case 0 and in case 1 that a very cold temperature, 65-degree air is the injection temperature, there's a lot of space in there that's 65 degrees air, and that's not necessarily providing a high level of thermal comfort either. Case 2 and case 3 are versions on a similar. There's still half the air volume is being put in at the bottom, and then for case 2, we've got some spill air that's coming out onto a series of the balcony circulation areas. And then case 3 is showing the reduced air at the bottom and then supply air directly along the glazing. Interesting. So this then leads us into thermal comfort. I think that bell was a 5-minute bell, right? Okay. And you know, as I said before, comfort ultimately is what we as mechanical engineers are trying to deliver to the occupied space so that people feel comfortable in a very habitable environment. Thermal comfort actually is a very challenging thing to try and do inside any space because there's a lot of different things that are going on and a lot of different things that variables that we have to take account of in terms of comfort expectations. There are temperature issues, both air temperature as well as mean radiant temperature. There's humidity issue. There's the air movement and speed and direction that plays a role. And then there's a couple of personal issues related to the metabolic rate, what's the activity level of the people that are occupying the space, and then the clothing level. You know, are they wearing, you know, suits and ties like too many of us are wearing here, or you know, are they in something a little bit more thin and comfortable, as the case may be. You wouldn't have a mechanical engineer up here without us showing our psychrometric chart. So we've got our ASHRAE Standard 55 psychrometric chart, which is showing the thermal comfort zone, both in inch-pound and metric units. This is from the most recent ASHRAE Standard 55 2010 version. And generally speaking, there's a thermal comfort zone. There's actually 2 of them here with different clothing levels, which if we can maintain the temperature and relative humidity within those zones, then that will equate to an 80% positive reaction from the occupants in that zone, 80%. So that's our goal, to make sure 80% of the people are happy. Now, there's a couple other things that sort of come into play in all spaces, but certainly within Atria. Airspeed, and one of the previous speakers actually started getting into this. There's an airspeed allowance if you've got an elevated temperature, especially a elevated mean radiant temperature. But if you are moving air across that person or persons, then there is a cooling effect, even though the air temperature within the space isn't changing. And it's simply almost like a reverse wind chill. So the skin wettedness is dried, and it provides that occupant with a sense of thermal comfort. So there are issues related to that. Now the reverse of this, of course, is that too much air movement, too high a velocity creates thermal discomfort because it becomes a draft. And again, you're trying to sort of maintain an appropriate thermal comfort sensation for people who have essentially different expectations. And then the other thing with regard to an atrium is there is a radiant temperature asymmetry. Now what this has to do is with the fact that people have different thermal sensation at different parts of their body as a result of various different factors. And the radiant temperature asymmetry, when you have a glazed wall or a glazed roof or something like that, warm ceiling, there's an impact on that person's thermal comfort. So a big glass wall that is not being kept to a certain degree thermally neutral in a high solar gain situation creates a lot of radiant temperature asymmetry and really sort of requires some additional attention to make sure that you're maintaining thermal comfort within that atrium. And then sort of the final engineering slide that I've got here from ASHRAE Standard 55 is really the ASHRAE thermal sensation scale. So you can see that it goes from +3 to -3 in terms of thermal comfort theory. The idea here is that people will vote, usually +2, +3, -2, -3 if they're thermally uncomfortable. So you're looking for something in the slightly warm to slightly cool category. And that gives you then a sense of where you need to be in terms of predicted mean vote and predicted person dissatisfied. Now coming back to those CFD animations, I've just got a couple of snapshots here, one of temperature distribution and then one of predicted mean vote. Here's what those temperature stratifications look like for the 4 different cases. And you can see that you get a lot of cold air in that base case because you're really punching a lot of air in there to offset that load. And so the whole space is certainly at the bottom not very comfortable. It certainly gets reasonably comfortable in the balconies up at the top. And then as you sort of move from left to right, you can see the variation that you get in terms of what happens from a stratification perspective for the 4 different alternative air distribution strategies. And then when you equate that to the predicted mean vote, which again we want to be sort of in that green to very light blue color, it really sort of, it tells you that run 2 and run 3 are the ones that we're looking for as a way of maintaining thermal comfort in the specific occupied spaces. All right, so a lot of stuff going on there, and trying to balance all of that and trying to do it in 20 minutes becomes a real challenge, certainly for us as designers. The successfully performing atrium balances light, whether natural or electric, balances air, again, whether naturally delivered or mechanically delivered, balances energy and water as a means of heating and cooling. And if we do our jobs right, at the end of the day, we end up with a collaborative and beautiful and thermally comfortable environment. That's okay, yeah. I've got nothing to say to these slides necessarily. It's just some nice atriums that sort of throw in. And apologies to those architects in the room if I didn't get one of your projects. Thank you.
I think we've got time for one question. Is there any questions at all out there? Okay, I'll ask a question then. So Robert, you talked a lot about the environmental challenges and opportunities there. Do you feel Atria have a social role to play in high-rise as well?
Well, I think the fact that I probably presented more the atrium as the lungs of the building than as the heart of the building, but absolutely. I mean, it is from a social function perspective, all of the stuff that I talked about here with regard to the balance of energy and light and air and whatnot, all of that comes down to making it habitable so it can be the social engine of the building, right? Whether it's a single atrium, whether it's a series of interconnected atria, whether it's a sky garden, which essentially is an elevated atrium. Yeah, I think this is absolutely the opportunity for it to play a huge role in terms of the social success of a building.